Howdy folks, and welcome to my channel. In this series, I'll be providing you with tutorials on the workflows involved in experimental seismology, as well as the science behind them. When it comes to experimental seismology, you guys might be thinking about applications like Petrel or similar industrial applications. These applications are actually multidiscipline, Mary G. Fly platforms that come with a lot of functionalities that we are, as researchers or students, could really benefit from. However, these applications are not easily accessible to us and independent researchers or students due to strict licensing restrictions. On top of that, these applications aren't typically transparent enough in terms of their algorithm implementation, due to their closed and proprietary nature, making them unsuitable for educational purposes. On the other hand, as researchers, we're always driven to innovate and create new workflows and algorithms. However, these applications don't really allow for contributions from independent researchers, not only because of their closed and proprietary nature, but also because of the fact that these applications are usually written in C++ and C#. And this deep learning, careful of these languages, makes it really difficult for researchers to contribute to these applications. Speaking of languages, Python is now the standard language for data science. Scientists worldwide use it to develop algorithms and workflows, often publishing their work on platforms like GitHub and Kaggle. With the advancement of science, machine learning and neural networks have become an inseparable part of research workflow. Python libraries like Petrel and TensorFlow have become the industry standard for world network and machine learning development. This shift is causing commercial applications to struggle to keep up with the state of the art. Now, some of you guys might be wondering about the performance and speed of algorithms that are implemented in Python. After all, Python isn't the fastest language out there. But here's the thing: over the past few years, we've seen amazing advancements in computer science, specifically in GPU acceleration and parallel processing. By leveraging technologies like CUDA programming and libraries like Cyton and Numba, you can actually create algorithms that run just as fast as the ones you can find in commercial applications. Now this got me thinking. What if we had a platform that is built on top of Python, so researchers could easily contribute to it? The idea is to make it completely transparent, so everybody really knows what's going on in terms of the underlying science behind the algorithm. Some work which gives the students an amazing learning opportunity. And since it's a GUI platform, it makes everything super accessible. Whether you're a student just starting to code or an advanced researcher, you can easily work with advanced visualizations, run neural networks, or use any of the algorithms that the community has contributed. Really powerful thing about making this platform community-driven is that it creates this comprehensive ecosystem where researchers can contribute their workflows and algorithms, get recognized for their work, and instantly make their innovations available to everyone. It creates this dynamic environment where science can rapidly move from research to real-world application, because everything is accessible, organized, and reproducible. So at the end of the day, what we have here is a comprehensive GUI platform that is driven by the community, accessible to everyone, and finally, fills the gap for all the scientists and students who've been left out because they couldn't access these expensive commercial applications. Now that we've talked about size, and we actually know what it's all about, I have a quick tutorial for you, just to give you a taste of what's to come. So, as you guys can see on the left, we have the Petrel application ready to go. And on the right, we have our very own community-driven platform sizing flow. So I've already gone ahead and loaded the same size make image into both platforms, and right now we're looking at the first inline slice of that image. Now, what I want to show you guys today is Petrel's Geobody extraction module. Pretty cool feature that lets you guys click on any size, make reflector you want, and it automatically extracts it throughout the entire 3D image. This is actually a huge deal, guys, because without automation, doing this manually would take a practitioner months to get right. You'd have to interpret each slice one by one, in both inline and cross-line directions, which is an incredibly time-consuming and subjective task. So let's see how well it works. And then I'll show you how Size My Floor handles the same task. Alright, let's start with Petrel. I'm just going to click on this reflector right here. It's got a really complex topography, as you guys can see. Let's see how Petrel handles it. And there you go. It extracted the reflector, no problem. Now, let's do the exact same thing inside me. Hello, here we go. Alright, now let's compare them, side by side. Take a close look at the results, guys. What do you think? If you ask me, Petrel's extraction looks a bit incomplete. It looks like the algorithm couldn't quite all through with the reflector because of the complex topography, and it missed this part. But if you look at seismic flow extraction, it's actually following the entire reflector across the image. Of course, this is just a small preview of what's coming next. In the next episode, we're going to dive into the science behind these algorithms. Do more head-to-head comparisons between petrel and cyclone flow. So if you found this interesting, make sure to like the video. Hit that subscribe button and turn on notifications, because there's a lot more where that came from. And hey, if you have any thoughts or suggestions, drop a comment down below. Also, feel free to reach out via email if you're interested in contributing. And as always, thanks for watching, and see you in the next one.